Hi everyone and welcome back to the Stats Show. So today we're going to talk about building linear models where we have categorical predictors. Up to this point we have had continuous predictors, or also known as covariates. We did a simple linear regression, which is when there was just one predictor in the model, and then we did multiple regression where there were multiple continuous predictors in the model. And again, traditionally that's what's referred to as a regression or a multiple regression. And now that we're going to start dealing with categorical predictors, we're going to go into what is traditionally referred to as an ANOVA. As I've mentioned before, that naming convention is a little unfortunate because ANOVA implies that there's some other type of different analysis that's being done, whether or not you have categorical or continuous predictors. And that's not really the case. As we'll see, they're all just an analysis of variance on a general linear model. And so these naming conventions of, regression, multiple regression, ANOVA, and then soon we'll talk about ANCOVA and nested ANOVA and factorial ANOVA. Those really tell more about the design of the study than they do about the analysis, because as we'll see, all of these analyses are essentially the same, and there's really no difference between an ANOVA and a multiple regression. So those words, it's worth knowing those words so you can communicate to the rest of the world, because not everyone's as pedantic as I am. But those words really tell us more about the design of the experiment than they do about differences in the analyses, because there's not really that big of a difference with how we're going to put these models together. And so we're gonna start with a very simple model where we have a categorical predictor. So again, we've done the continuous predictors, but now we want to have a categorical predictor, and this is a really kind of common setup that you would have if you ran an experiment. You might have a control group, and then you might have two treatments or something like that, where you have your covariates that are in categories themselves, and you want to come up with a model that'll explain the difference among those categories or those treatments. And so categorical predictors are described as having levels. And so let's take a really simple example. Let's say that we were to run an experiment where we had a control and a treatment group. If we have just a control and a treatment group, then we would describe that as having two levels in our for our design. And that'll become important when we start thinking about how many degrees of freedom we should have, and how many parameters we might be estimating. But let's just start off and just kind of play with some made-up data real quickly. I'm going to make myself small, as I want to do. Okay, so this is from the code that was posted. Again, I'm going to set the seed so everybody has the same data if they're playing at home. And I'm going to just simulate data where I have a control group and I have a treatment group. I'm going to combine those two things together, create a vector that says control and treatment. So ultimately what I'm going to do is I'm going to have the data that are in this type of a format. And this is what it would look like if you had input all the data in using something like Excel and then read the CSV into R. And so here we have our groups. We have two different groups. We have a control group and a treatment group. And we have our data, our DAT. And this is all of our raw data. And we can see here that we had 25 replicates in the control group, and we have 25 replicates of the treatment group. So we've all simulated our data now, and we should all be playing on the same page. And so the first thing we can do is we can have a look at our data. And so I'm going to call up a function that we haven't played with yet called boxplot. And I can set up a boxplot simply by putting a formula in there that would look very much like a linear model. So I can say that dat is some function of groups. And then I'm just going to make sure that the figure looks pretty. LAS equals 1, so that way everything looks pretty. Now I probably should make this a little bit bigger so we can take a look at it. Oh, come on. What did I do? Oh, that's what I did. Error, warts and all. Okay, so here is a graphical representation of our data. And so we haven't really talked about box plots, so I want to really quickly introduce box plots. Box plots are not used as much as the familiar bar plot that I'm sure everyone here is familiar with, where you just have the bars and then you have a little error bar within those bars. And those are fine. There's nothing wrong with bar plots. I personally don't like them as much as something like a box plot, because bar plots are really only communicating to the reader your parameter estimate and the uncertainty around your parameter estimate, whereas box plots are explicitly plotting your actual data. Okay, so what is the anatomy of a box plot? So the first thing we'll see here is this line that's going through the box plot, okay? And that is a lot of times referred to as the hinge, if you will. And the hinge there with the standard box plot is the median. So if I were to plot just the median for the control group, that's exactly where it falls. It falls right on that line. And now, once you have those hinges on either side, you have this box. And what that box is going to do is it's going to capture all of your actual data that's between the 25th percentile and the 75th percentile. So 50% of your data will fall within this box right here, okay? And so if we were to, go ahead and I'll put some green dots on there now. And so this is the 75th percentile, this is the 25th percentile of the data. So that's the box, that's 50% of the data, and the next thing is what I refer to as the whiskers. I guess formally this is referred to as a box and whisker plot. And what the whiskers capture are the data that are obviously outside of that inner 50%, and the whiskers will extend as far as what's called the inner quartile range. So the inner quartile range is the range between the 25th percentile and the 75th percentile. The whiskers themselves will extend as far as 1.5 times that inner quartile distance, or they'll stop at the most extreme value that is in your actual data, okay? And then for data that fall outside of that, it'll actually plot it as a dot or as a point, okay? And so these are what are often referred to as outliers. Outliers aren't necessarily bad. It's just nice to look at them and be aware that they're there, because they could actually be influencing your analyses. And so again, I like box plots, especially as an exploratory data analysis tool, because it gives you the opportunity to kind of have a graphical representation of what your data actually look like. Whereas if you're doing something like a bar plot, all you're really doing is showing what the mean is and what the uncertainty is around that mean. And again, that mean and that uncertainty around the mean, like the standard error, will only mean what you want it to mean if the mean means what it should mean, which means that your data should be normally distributed, right? And so the box plot is a nice way to kind of look at the symmetry of your data and to get an idea of how good you might feel about it. So anyhow, that is our box plot. Those are the data that we are interested in analyzing. Right, okay, so what are we ultimately going to want to do if we want to compare this and we want to do it in our familiar linear modeling framework? Well, what we're going to want to do is we're going to want to think about the relative amount of the variation that's explained between the groups, and then also think about how much variation are we failing to explain, right? The error term. And we can do this, and it'll resemble very much what we did when we did the very long, cumbersome first attempt through the simple linear regression. And so the first thing I can do is I can think about what is the mean of the control group, what is the mean of the treatment group, and then what is the grand mean. Okay, so I have the code here where I'm going to come up with the mean of the control group, the mean of the treatment group, and then the grand mean. And so if we want to think about what portion of the variation are factor levels explaining, the control in the treatment group, we can do that very similarly to how we did it with a simple linear regression. Remember, we had all of those expected values, and we took the sum of the squared deviations of those expected or fitted values to the grand mean. And that's how we came up with the sums of squares associated with our model. And so we can do the same thing here. So I'm going to just change this plot a little bit. So we're just looking at the means. Now these are just the means here that we're looking at. And we can take this red line here, which is the grand mean. And then all we're going to do is the mean for the control group, that is the expected value for the control group, and the mean for the treatment group is the expected mean for the treatment group. So what we can do is we can look at the difference of the control group to the grand mean for each observation. There were 25 observations, so we're going to want to take this distance and we're going to want to square it, and then we're going to do that, we're going to take the sum of that 25 times. And then that is going to give us the sums of squares associated with our factors that are in the model. And so basically we're going to take those distances, we're going to square it, and then we're going to multiply that by 25, just because it's easier to multiply it by 25 than to add it 25 times. But adding it 25 times, if you want to write extra long code, I'm all for writing what code, so go for it. But it's easier to just say 25. And so let's go ahead and do that. And so here's my sums of squares among groups. And again, it's going to be the mean of the control group minus the grand mean. I'm going to square that. And then I'm going to multiply that value by 25. Likewise here, I'm going to take the mean of the treatment minus the mean of the grand mean. I'm going to square it, multiply it by 25. And so this should give us the sums of squares among groups. Okay, so it's 45.19711. Feeling good, feeling really good. Okay, so that's the model sums of squares, and then we can continue to think about this the same way that we did with a simple linear regression. Now we want to deal with the amount of variation that we can't explain among groups. And to do that, we're going to take all of our observations within the control treatment, and we're going to look at the sums of squared deviations of all of those observations from the mean of the control group. And likewise, we'll look at all of our observations from the treatment group, and we'll think about the sums of the squared deviations of all of those observations from the mean of the treatment group. And essentially, we're doing the exact same thing we did with a simple linear regression, where we're basically just taking the square of the residuals, right? That's all it is. It still is called the residuals. And so let's go ahead, and here I have a pretty plot just to make sure that we're clear on what we're doing. There's all of our data points for the control group. There's all of our data points for the treatment group. And what we're going to do is we're going to take all of those distances within those, and we're going to take the sums of the squared deviations of all of those observations from the mean of that group. And so I'm going to go ahead and I'll cut and paste the code that we all have and that we're all playing with at home. So I have the sums of squares for the control is, again, simply the sum of all of our control data from the mean of the control data squared. We're going to sum up all of those for the control group. We're going to sum up all of those for the treatment group. And then we're going to just add all those together, because that'll give us the total sums of squares of the error. And again, the sums of squares of the error, or the residuals, that is just simply the variation that our model is failing to capture. So we go ahead and we do that, and now we have the sums of squares of our error. Okay, so we're back to kind of thinking about building an ANOVA table, right? We could do it back on the board, but we've already done this a few times. We don't need to. I mean, repetition works, but let's not get crazy with the repetition. So then next we need the total sums of squares. And the total sums of squares could either be all of our data from the grand mean, or we could just, again, sums of squares are additive, so we could just simply say that the sums of squares among groups plus the sums of squares of the error term, that's going to be our sums of squares total. So let's go ahead and we'll do that. All right, so what do we got? We got, where am I? Where am I? We have the sums of squares among our groups. We have the sums of squares of our error, and we have the sums of squares total. And so just as we did before, I mean, this is what analysis of variance is doing, right? The next thing that we have to do is we want to take those sums of squares and turn them into variance components, or mean squares. And to do that, we take our sums of squares and divide it by the appropriate degrees of freedom. And so how do we calculate our degrees of freedom? Very similarly to how we did when we did it as a simple regression. So the degrees of freedom associated with our sums of squares among groups, right? We have two different groups, we have two different levels, and we're going to take that minus 1. That is the degrees of freedom that we're going to have. So if we have two groups, we have 1 degree of freedom. And as we wanted to calculate the mean squared among our groups, we can go ahead and we can do that. So I'm going to do that right now. There it is. Mean squared among groups is the sums of squares among groups divided by 1. And then the mean squared of the error term is going to be the total number of observations minus the number of parameters we have in the model. So again, just like we did with when we were constructing the ANOVA table for a simple linear regression. And so we have 50 observations, and we've estimated 2 parameters. We've estimated the mean of the control group and the mean of the treatment group. So 50 minus 2 is 48. And so if we wanted to calculate the mean squared of the error, we would take our sums of squares of the error term divided by 48. And make sure that one's in the old RAM. So here's our mean squared of the groups, mean squared of the error term. Okay, we're using an analysis of variance to do the hypothesis testing. We want to think about the ratio between those two variance components. So we calculate our F statistic, which just as before is going to be our mean squared of the groups divided by the mean squared of the error term. And so let's go ahead and we'll do that. There's our F statistic. All right, there's our F statistic. And now all we need to do is calculate the p-value associated with that if we wanted to do null hypothesis testing. So to do that, we take the cumulative distribution function of an F distribution. We go ahead and we pop our F statistic in there. We have to give it 2 degrees of freedom. F statistic always has 2 degrees of freedom associated with it. The numerator is 1, because that's how many degrees of freedom we had with our model. And then the denominator is 48, because that's the number of degrees of freedom that we had available to us in the error term. 1 comma 48. And then of course we'll say lower tail equals false. So we go ahead and we do that. We get a 0.005728135. And based upon our alpha cutoff of 0.05, we would reject the null and accept the alternative hypothesis. Here the alternative hypothesis is there must be a difference between our control and our treatment group, because our model, where we model those as having 2 different means, is superior to the model where we don't estimate anything between those 2 different groups. Okay, so that's the basic setup of how an ANOVA is going to work and what we're going to do. And hopefully I've convinced you that it's really, really similar to how we did it when we did it with a regression. And so now let's go and let's really turn it into a formal linear model so that we can understand what the output is that statistical software packages are going to give us. So let's get ready and do that. Alrighty, let's think about setting this up formally as a linear model, as it were. And so we've already kind of gone through the basics of what we're trying to accomplish by putting these linear models together with categorical predictors. And how we are going to accomplish this in a more formal linear modeling way is we are going to use what is referred to as dummy coding. And yeah, it's called dummy coding. That's what we're going to do. So let's think about what we've done up to this point when we were playing around with it. So we were hoping that we could predict something, right? And so it could be ij, let's say. So it could be the ith individual in the jth factor. And the factors here that we're dealing with are control and treatment. And how we've done it up to this point is we said, okay, well, we have the grand mean, right? We have our estimate of mu, the grand mu. And then we had means for both temperature or for treatment and for the control group. And if you think about when we were calculating those sums of squares deviations, we were looking at the distance from that mean to the grand mean, right? So the mean of the control group to the grand mean, and the mean of the treatment group to the grand mean. And this is where the dummy coding is going to come in. So first of all, if you remember, we had our control and we had our treatment group, and then we had our grand mean. The distance from the control to the grand mean and the distance from the treatment to the grand mean, those are essentially our parameter estimates. They are telling us how different those control group or those different groups are, the control and the treatment group, from the grand mean. And so this is how we're going to end up building our model, but we're going to include what's called a dummy variable. And we'll see in a second why that'll make sense. So let's say that we are going to have, beta 1, which is, let's say that that's going to be our control group. And then we're going to have a dummy, big dummy. We're going to have dummy 1 for the ith and jth individual. And then likewise, we're going to have beta 2 with a dummy for the ith and jth individual. And so right now what we can do is let's think about what this looks like, and then we'll get into exactly what the heck these dummy things are. Jim, you're just saying dummy and you're not telling me anything. I promise I will. So we're going to start with our grand mean, which I have no recollection of what our grand mean was. Wow, that's just not being very prepared, is it? Where is that? Where is our grand mean? Mean grand. That was, where is it? 11.61. Yeah. So for our purposes, we'll say it's 11.6. Everyone starts at 11.6. If you're in the control group, let's say that that's our first factor level, which it will be because computer programs generally do it alphabetically, and C comes before T. So our first factor level will be the control group. The control group was negative 0.95, less than the grand mean. And then let's keep our dummy here just for a second. Dummy. And then for the treatment group, it was 0.95 greater than the grand mean times the dummy. Okay. So now we're getting really close, right? We kind of understand that everything now is being relative to the grand mean. If you're in the control group, you're 0.95 less than the grand mean, and if you're in the treatment group, you're 0.95 greater than the mean. And so now is this dummy stuff. Let's talk about this dummy stuff. Dummy stuff is essentially coded as either a 0 or a 1. And so, for example, if we were interested in coming up with the expected value for the control group, our dummy coding would be a 1 and a 0, because you're in the control group, so you're going to multiply negative 0.95 times 1, which means that it's 0.95, right? Or negative 0.95. And you're gonna take that and add it to the grand mean. So 11.6 plus negative 0.95 times 1, that is going to be the expected value for the control group. For the treatment group, you're going to add 0.95 times 0, which means that it's going to drop out of the model. And so likewise, if we were interested in the expected value for the treatment group, our dummy coding would look like this, where we would multiply this parameter now by 0, so it essentially drops out of the model, and then here we would multiply this by 1, so it stays in the model. So a useful way to think about it, how I think about it, is you can think about these zeros and ones as being switches as to whether or not something is turned on in the model. And so with this dummy coding, if I wanted to know, what is the expected value for the control group? It would be 11.6 minus 0.95 plus 0, right? Because our dummy coding for the control group would be 1 and 0. And so basically we're just flipping switches saying this is going to stay on in the model when we're interested in the control group, this is getting turned off. And likewise, if we wanted to know the treatment, what the expected value for the treatment group was, we would again start with the 11.6 plus negative 0.95 now times 0. So plus 0 plus 0.95 times 1, which is 0.95. And that's how we're coming up with our expected values. Okay, so that's what's meant by dummy coding. And you can think of it as a way of just turning on and off different parameters in the model, whether or not you're in that group or not. And so this type of a model that we have right here is what's referred to as a linear effects model, which is totally fine. Some statisticians get a little queasy, I guess, with this because we only have 2 factor levels, yet we had to estimate 3 parameters. So we have more parameters than we have actual things that we're trying to model, which some people don't feel very good about. For the hypothesis testing part, it makes no difference at all, but there is actually a solution to this problem, and this overparameterization problem, in quotes, if you really want to think about it as being a serious problem. And that's what's known as a cell means model. And this is the approach that all statistical programs that I know of uses. Yeah. And so how the cell means model works so that it's not over-parameterized is that it's going to lump together our first factor level and the mean. It's going to put that all into one parameter, which means that everybody's going to start out as, in this case, the control group, and then we're going to see how much we're going to tweak the control group, or how much those values are going to be changed if you're in a treatment. And so this model will look something like this. And so now we're only estimating 2 parameters because what we've done, this should look really familiar, right? Because this is what our simple linear regression looked like. And so what we're doing is we're gonna ignore the grand mean, and we're gonna just set our first group, which is the control group, as the intercept. And so now this will be the mean of the control group, and then this parameter here will be the difference between the treatment group and the control group, and then we'll have our dummy coding. So if you're in the control group, the dummy is going to be 0, which means that all you have is the intercept, which is great because that would be the expected value of the control group. If you're in the treatment group, then this becomes a 1, and then you would start at, everyone gets an intercept. You'll start at the mean of the control group, and then you'll add some value to that, which will give you your predicted value. So let's just take a look at it in R, and I think that it'll become pretty intuitive as to what exactly is happening, hopefully. Okay, so where were we? Right, so we want to set it up as a linear model. So instead of doing all of this rigmarole, which of course you'll never do, we're going to set it up as a simple model. Model, what kind of model? Well, linear, that would be a good one. Let's do a linear model where we're trying to predict our DAT as some function of groups. Oops, what did I do? What the heck did I do? How did it do that? There. Okay, so we set it up just like we set it up when we set it up as a simple linear regression. Dat is some function of groups. So we go ahead and we do that. I'm going to load in that car library, library car, because we are certainly going to want to do marginal sums of squares when we're dealing with categorical predictors. Although in this case it wouldn't be as important, but it's a good habit to get into. And so let's go ahead and we can say, oh, let's do our ANOVA on that. And there we have it. It's significant. Notice that that's the exact same p-value that we got when we did it longhand by doing it within groups and calculating all those sums of squares. Here, we're just having the computer do it for us. Again, we know where these sums of squares come from. We know where the degrees of freedom come from. The degrees of freedom are the number of factor levels minus 1. We have 2 factor levels here, so we have 1 degree of freedom. And then for the degrees of freedom for the residuals, we have the total number of observations minus the number of parameters we've estimated. And in this case, we've estimated 2 parameters, an intercept and a slope. And let's go ahead and let's take a look at what our model looks like, right? Because we always like to interpret parameters. And this is a thing that sometimes throws people off, because when we're dealing with a simple linear regression type design, we understand what the intercept is and we understand what the slope is and then the relative importance of the slope. Here, it's not quite as intuitive. We have this thing called the intercept, and we have this thing called groups treatment. And again, let's remind ourselves what groups are. Oops. Right? You're either in the control group or you're in the treatment group. And behind the scenes, what R is actually doing is it's converting it into a factor. What the heck was that object called? Groups. Groups. So if I actually told it as factor, you can see down here, here's the 2 levels, control and treatment. Computer programs, generally, all the ones I can think of, will always just go alphabetically, and whichever one comes first alphabetically, that one is the one that's going to get the intercept, or is going to be the intercept. So let's go back and let's look at that. And so we have 10.668. That means that if we were to take the mean of our control, what did I call that? Oh, I'm killing myself. Control data. Okay. Control spelled correctly helps. Control data. And there it is. That's the mean of the control data. And now we have our slope estimate, our parameter for the treatment group. Okay, and so let's look at the mean of the treatment data. That's 12.5694. And if we were to take the mean of the treatment data minus the mean of the control data, that's where we're getting that 1.902 here, okay? So basically what that's saying is, for this model, if you want to interpret the parameters of this model, everyone starts with the intercept. Everyone will always have the intercept. So you can think of it this way. Everybody is a control. And then if you happen to be in that treatment group, you're going to take the value from the control and you're going to add 1.902 to it, and that will be the expected value for the treatment. Okay, so we have our parameter estimates, and again, how the dummy coding is working is you can think of it as a toggle, whether or not you're going to add 1.902 or not, based upon whether or not you're in the control group or the treatment group. And we could ask R kindly to show us what that dummy coding is actually looking like and what's happening behind the scenes using a built-in function called model.matrix. And then I'll go ahead and I'll put our model in there. And what it's giving us is a bunch of 1s and 0s. So everybody, and this would be individual 1. Individual 1 was in the control group, so it gets the intercept. And then its dummy code for this slope of 1.902 is 0. And so if you're in the control group, again, everybody gets the intercept, so it's 10.668 times 1 plus 1.902 times 0, which is going to be 10.668. And then if you were in the treatment group, your dummy code is a 1. And so what that means is, behind the scenes, essentially, this is just simply a linear regression. And we can prove that to ourselves by, let's go ahead and we'll set it up as a linear regression in the traditional sense. So I'm going to create something. I'm going to save my dummies. I want to save the dummies. Okay. So now I have all my dummies right there. And I'm going to set this up as a regression model. And it's going to be a linear model where I'm still, again, trying to predict the data. Except here, I'm just going to say all I want is this column of zeros and ones, because this column here is redundant, right? Everybody's got it. There's no variation there. But if you're in the control group, you got a 0. And if you're in the treatment group, you got a 1. So I'm going to go ahead and I'm going to take that second column of my dummies. Okay, now I have it as a regression model, right? It treated this as being a continuous covariate. So I'm going to go ahead and I'm going to do that. And lo and behold, the intercept is 10.668 and the slope is 1.902. That is the exact same thing that we got when we gave our the covariates as categorical factor levels, right, as groups. Here we're just saying, oh, well, we understand the dummy coding so well, we can just do it as a simple regression. And we could plot and see what is happening behind the scenes here. And so here's 0, here's 1, right, because that's the only dummy coding that's involved here. Here's all of our data. And then if I went ahead and I did an AB line of our model, AB line, it looks something like that. That is actually what's happening behind the scenes, which means that an ANOVA, not only is an ANOVA misleading because it's only referring to the experimental design more than the analysis, because ANOVA encompasses all of these analyses for linear models, but here we've set it up as a regression, and we're getting the exact same answer because they're all actually the same thing. As long as you understand that they're all linear models, that's really all you need to know, and then you're ready to go. And so again, our expected value for the control is whatever it was, 10.688, and then our expected value for the treatment, which has a value 1 here, is 1.902 greater than 10.688. And that's it. It's really that simple. Yeah. So let's take a pause for a momento, and let's think about when we have more than just 2 factor levels, because at this point we only had a control and a treatment, and it kind of makes you wonder, well, why didn't we just go ahead and do a t-test? Spoiler alert, you probably would want to do a t-test, but we'll get to that in a second. Okay, so as I mentioned, for this type of a situation where we only have 2 groups, right? We had a control group and a treatment group. This is a situation where we would probably want to use a t-test, because recall that now the default in the t-test does that Welch-Satterthwaite correction for degrees of freedom in case the variances are different from one another, which will probably give us a little bit more of an honest statistical approach to the problem, because it would be able to account for that. When we set things up as a linear model, we are assuming that there's homogeneity of variances. And so, like, if we were to do, like, set it up as a t-test, Jim. So we have our control data. Oh, come on, Jim, get your act together. And we got our treatment data. We do that, and you'll see that we don't have 48 degrees of freedom. We have 47.956 degrees of freedom, which means that we got penalized a little bit because our variances were a little different between the control and the treatment data. But it's entirely possible that there could be a whopping difference in the variance, which would mean that, oh, we don't feel good about doing that as a linear model, as a classic ANOVA, which would make the t-test more appropriate. I will point out that if you were to do the t-test and you said var dot equals true, remember that was the argument where it was the old school t-test without that correction. If we were to do that, now we have 48 degrees of freedom. There's our t statistic. If we were to square our t statistic, yeah, neat. There we go. And then if we were to go back and look at our ANOVA, you'll see that the square of our t is identical to what our f is, and we got the identical p-value. And in this case, because the variances are so close to one another, it really doesn't affect our p-value that much, right? It certainly doesn't affect it when it comes to hypothesis testing. But I just wanted to mention that if you actually do have two groups, it certainly would be more appropriate to just analyze those data as being a t-test problem, because it's more than just a t-test that we do. It's that t-test that does that Welch-Satterthwaite correction for degrees of freedom. So it would be the more appropriate way to model that. All right, so that's why t-tests might be good. And now let's think for a minute why t-test might not be the best option. So why not just do a bunch of t-tests? Why is Jim all hating on t-tests? Well, t-test clearly would be the appropriate analysis if you were only comparing two groups. Where a t-test would become problematic is if we had more than two groups. And as we'll see, the reason why it'll become problematic is that it's going to be more difficult to control our type 1 error rate. So I'm going to make myself small again. That's all Jim does. He's got some serious self-esteem problems. Let's see here. Okay, so I'm going to set up a scenario, as I'm wont to do, where let's say that we had three groups that we were interested in comparing. And I have cleverly called these Group A, Group B, and Group C, okay? And so we're interested in comparing those three groups. And yes, in principle, you could do it as a bunch of t-tests. So I'm gonna go ahead and I'm gonna do a bunch of t-tests, okay? So here's a t-test comparing A and B, significant. Here's a t-test comparing B and C, significant. A t-test comparing A and C, not significant, okay? And so that seems intuitively that would all be fine. But here's the problem, is that if we're doing multiple tests on the same data, which is what we are doing here, we are not going to be effectively controlling our type 1 error rate. Remember that as frequentists, we are striving to be wrong 5% of the time. But if we start double dipping into the same data multiple times, we are going to increase the probability that we would just get that significant answer 5% of the time. And so when we do multiple t-tests, we need to do some kind of a correction. And what corrections will do is it'll essentially rescale our p-values so that we are accounting for the non-independence across all of those things, across all those comparisons. And how we do this, the standard, most conservative way to do it is to use what is called a Bonferroni procedure or a Bonferroni correction. And how the Bonferroni correction works is you simply take what your threshold is for statistical significance. And so if we were to do things in a very kind of standard way, where is a marker? If we were to do things in a kind of a very standard way where we have alpha equals 0.05, right? That's our type 1 error rate, which we want to be happy with. To do the Bonferroni correction, to be significant at 0.05, if there are three comparisons, so in this case here, there are three different groups that we're comparing, group A, B, and C, we would have to take that alpha value divided by the number of comparisons. And so in our case here, it's 0.05 divided by 3, which means, ow, that was my knee, which means, killing myself here, what the? Which means to be significant at 0.05, our p-value would actually have to be 0.0166, okay? So the threshold now has gotten a lot lower, which is why Bonferroni is considered to be a bit conservative. But that's what we would have to have our p-value to be significant. Now, based upon this little bit of arithmetic here, you can see that the other option would be, since there's three comparisons involved here, is to take each of these p-values and multiply them by 3. So our p-value now associated with the comparison between A and B is no longer 0.01735. That's our p-value, 0.052, which means in principle it is not significant, right? Because if we're gonna hold to that 0.05 as being the magic number for statistical significance. And then likewise, we could look at the p-value associated with B versus C. And we could multiply that by 3. And now that p-value becomes 0.007. So even after the Bonferroni correction, the comparison between B and C is still significant. And then the comparison between A and C, it doesn't really matter because it already was not significant. So we don't really care. We don't need to do a Bonferroni correction on that. So that's the Bonferroni correction. There is a slightly less conservative version of the Bonferroni correction, which is called sequential Bonferroni. And it's also called the Holm test, H-O-L-M, or the Holm-Bonferroni correction. And this is going to be slightly more powerful than the strict original Bonferroni. And so you're going to be less likely to commit a type 2 error. And how this works is you rank your p-values from lowest to highest. And so in our case here, what are our p-values? We got 0.39, we got that one, and I guess I already have it here. We got that one, right? So right here are our 3 p-values. So the first thing we would do is we would rank them. And what we would do is we would start with the lowest p-value. And at the lowest p-value, there's 3 possible downstream comparisons that we're doing. So for the first p-value, we are going to do the old school Bonferroni correction, right? Which means that this would turn into that. Okay, so that's going to be our p-value for that. That's going to be our adjusted p-value. Our second p-value now, since we've made it past that first hurdle, you can think of it as like you're running along, you've made it past the first hurdle, the first thing is significant. Now when you get to that next p-value, you only consider the number of subsequent comparisons that are going to be done. So here, it would be 2. And so now our p-value is 0.0347. And if you remember when we did the strict Bonferroni, it was just barely over that 0.05 threshold. So again, we have more power with this Holm procedure for correcting. And then the last one, it just stays the same. Okay? And so that's how a Holm correction works. A Holm correction, as soon as you're going from the smallest p-value to the highest p-value, as soon as you get to a p-value that is no longer significant at 0.05, you stop. You don't do any further corrections, and all the rest of them are considered to be not significant. And so there is a function that will do this for us called p-adjust. And you can see that the arguments here, the method is the first one here, which is the Holm correction. So it's automatically doing that sequential Bonferroni. Again, sequential Bonferroni and Holm are the exact same thing. And so if I were to take all of my p-values and put them into that function, so here's my vector of p-values. You don't even have to worry about putting them in order for the function. It can figure out how to do that itself. And then I'm telling it that I want it to do a Holm correction. And here are the updated p-values that I have, right? So that 0.735 became the 0.0347, which is the same thing that we got here. And the 0.0024 became 0.0073. And then again, the highest one, it just stops, okay? And so the p-adjust function is a useful tool if you ever have to do this kind of a correction. Now, there are certain situations where you might feel better about just dealing with the fact that you have to do this correction and doing a bunch of t-tests. And that might be a good decision when you have an enormous number of or an enormous difference in the variances among those groups, because with an ANOVA, the assumption is homogeneity of variances. And if it turns out you have three groups, but they are whoppingly different in their standard deviations, maybe you don't feel comfortable modeling that as having the same variances. And so that might put you into a situation where you have to do a bunch of paired t-test and then do the correction. It doesn't happen terribly often. But these types of corrections do come into play quite a bit whenever you're dealing with a situation where you are double dipping into data, basically, where you're using the same data to test multiple statistical hypotheses. If you're doing frequentist statistics and you want to keep your type 1 error rate at 0.05, you have to do some kind of a correction. And so one place where that comes up frequently is when people do what are called GWAS studies, which is genome-wide associational mapping of various loci across the genome. And maybe you want to find loci that are, correlated with, say, cancer or something like that. And you have 10,000 different loci, and you're looking at the correlation between the occurrence of that loci being some kind of, some polymorphism or whatever it might be, and the incidence with cancer. And you would do 10,000 different correlations. You would get 10,000 different p-values, but then you have to do a whopping correction. And there's really no other game in town but some flavor of something that's similar to a Bonferroni correction. Now, clearly, those of you that are playing around with genomic type stuff, you know that there are probably more elegant solutions to doing that, but the traditional way that people did GWAS was to just do a big whopping sequential Bonferroni correction to identify loci that were candidate loci that might explain, the occurrence of some kind of a trait. And so whenever you're double dipping into data, you always have to think, okay, are these truly random variables, or have I already analyzed them once? Because if I've already analyzed a part of them once, you have to do some kind of a correction. But we're not going to worry about that, because we're going to stick with our old friend, the linear model, where we don't have to worry about such things. And so let's go ahead and let's think about how we would go ahead and set this up as just a big linear model. So again, I have my A, B, and C. So I'm going to just create a vector called treats, which are going to be the different treatments. Okay, so I'm just creating a long vector of A's, B's, and C's for this. And then I have my responses, which is just simply all the data. Again, if you were to upload this data from an Excel spreadsheet, it would probably look something like this, where treats equal treats and response would equal response. And it would probably look something like this if you read it in from a CSV file, right? This is what the data would look like when you put it into Excel or whatever your favorite spreadsheet might be. And so all we have to do then is make a model, which is going to be a linear model. Some function of treats. We'll go ahead and we'll do that. There's our model. There's our parameter estimates from our model. And just like before, it's doing that cell means model. So you'll notice that there's a slope for treatment B and there's a slope for treatment C. Where's treatment A? Well, treatment A is the intercept. And so if we were to look at the mean of A, it's 59.4. And because we understand now how to interpret these parameter estimates, we could eyeball that and say, I bet that the mean for B is 59.4 minus 14.5. So let's just let the parameters tell us what the answer might be. 44.9, and now let's look at the mean of B, 44.9. And likewise, treatment C then, I would expect the mean for treatment C to be 5.6 greater than 59.4 plus, 65. And the mean for C is indeed 65. Okay, so we interpret those parameters the same way as before. As before, the coding in the background, it's all being done with dummy coding. So we can look at our matrix model.matrix of our mod. And here's all the zeros and ones, okay? And so again, everyone gets the intercept. Everyone is starting out as a reference, their reference being treatment A. And if you're in treatment A, then you get the intercept, which is 59.4. And then you say minus 14.5 times 0, so that gets dropped out, plus 5.6 times 0, so that gets dropped out, right? And again, we can think about the dummy coding as being little switches that are being turned on and off. And then just to convince ourselves that, hey, this is nothing more than just a linear regression, I bet, we can keep our dummies as an object. And then we could set it up as a multiple regression. And again, multiple regression is really just describing the experimental design. It's not the analysis, because this is an ANOVA, darn it. Why is Jim doing a multiple regression on that? It's freaking me out. Well, because that's all it is. So it's a linear model where the response is going to be some function of what? Well, the second column of dummy column 2, plus dummy column 3. Okay, so it's just, again, it's a multiple regression where the possible values are zeros or ones. There's not a lot of continuous stuff going on in there. It's just a 0 or a 1. We go ahead and we run that, and then we can look at that. And we get the exact same parameter estimates, except this time we explicitly modeled it as a multiple regression, whereas when we did it this way, our friend R did all that for us. But the parameter estimates are the same, and we interpret the parameter estimates the exact same way. And so again, we could do an ANOVA on that. And then we'd say, okay, there is some kind of a difference there between our treatments. I wonder what that could be. All right. Well, let's think about how we would maybe go about finding a difference of where those differences are. Oh, actually, there's another cute little thing I can do to kind of convince you that it's nothing but a multiple regression under the hood. So I'm going to just make a plot here. I need to do a bunch of code here. Right? Yellow. All right, scatter plot. Okay, so here we have 0 to 1, that's group C. We have 0 to 1, that's group B. And here's our response variable, okay? And so what we're doing when we're setting this up, right, because it's either you get a 0 or a 1, depending on what group you're in, if you think about it as a multiple regression. What we're doing, what our model has done, is it's essentially just fit a plane to those 3 different groups. And this slope here is telling us the difference between groups A, B, and C, which again are captured in, where is our model, which is captured in our parameter estimates. So yeah, so again, we've done the ANOVA, we got our p-value, we're like, yep, there's a difference between treatments. And now what we need to do is we need to think about how do we go about figuring out where the important differences are. Because all we know now is that A, B, and C, something in there is different. But we don't know if A is different from B and is different from C, or if maybe A and B are the same but different from C. And so to do that, we got to start thinking about what are referred to as post hoc tests. And that's what we will. We got our model, we did our ANOVA on the model. Something interesting is happening with treatments. Now what we want to do is we want to figure out where that interesting difference might be. And so this brings us to what are referred to as post hoc tests. And they're called post hoc because they're a test that is done post hoc. It's done after the actual analysis of variance. Once you've done the analysis of variance and it's indicated that there's something interesting going on with treatments, you can follow that up with a post hoc test to find out where those interesting differences might be. And there's 2 main categories of post hoc tests. There's what are called unplanned tests, and then there are planned tests. In general, usually unplanned tests are what people end up using because you don't have any a priori idea about where particular comparisons might need to be done. So with unplanned tests, and again, they're unplanned. There's no a priori hypothesis about the differences. There's a number of different flavors, and I'm going to mention just two. The first one I'm going to mention is what's called Fisher's LSD. And Fisher's LSD stands for least significant difference. And essentially what Fisher's LSD is it's a bunch of paired t-tests where you use the ANOVA mean squared error when calculating the t-statistic. This method is the oldest method. It's also the not recommended method. It seems like it's gaining a little bit of popularity again, and I don't really understand why. But it's considered to not be conservative enough, so it doesn't account for type 1 error rate as much as one would hope, because it's essentially a bunch of pairwise comparisons without doing something like that Holm or Bonferroni correction. There are some packages that'll do that. There is a package called LS Means, which I believe does it, and there's a package called Agricola that does Fisher's LSD. But I'm not going to even do it because I have no interest in it. I don't think that people probably should be doing it. As I said, there's a bunch of different flavors of post hoc tests that have kind of come in and out of fashion. The one that the majority of people use now and have used for about the last 20 or 30 years is what's called Tukey's, honest significant difference. So, piece of trivia, Tukey's the same person that came up with the box plots. So, how the Tukey procedure works is it's basically accounting for the non-independence when you're doing those pairwise comparisons. And so instead of going through the math, let's just apply it because we understand what it's going to do. And there's going to be two different ways in which we can do the Tukey's test. One is a really simple way that's a built-in function in R, and then another one is a little bit more complicated to set up, but we're going to want to learn how to do that more complicated one to set up because it has a lot more flexibility for other types of multiple comparisons that we might be interested in doing. But let's start with the built-in function, which is called Tukey HSD is the name of the function. Okay, it's part of the stats package. It's built in. And what it's going to want, the only thing that we're really going to need to give it is a fitted model object. And it says usually an AOV fit. So I don't think we've played with AOV just because there's not usually much of a reason to until now. So recall that we have our model, right? And we can look at our model. Here's our parameter estimates from our model. And we can also do an ANOVA on our model. But there's another function that we could use called AOV, which basically will do all the work required to do an ANOVA without doing the hypothesis testing part. And so I'm going to call up that function. It's AOV mod. And so, it's got the sums of squares. It's got the degrees of freedom. There's actually a lot of stuff in there. It's a list, so we can look at the names. Right? It's got all of these different things in here, what the levels are, the coefficients. It's got everything in there. The one thing that it doesn't have in there is an F and a p-value. So you can think of it as it's doing all of the analysis of variance without the hypothesis testing part. And so I'm going to just create an object called AOV.mod, so that way I know that I'm making an AOV object based upon my model. So again, that's what I'll get if I just type in that. But that's what the Tukey's HSD function wants. So if I type Tukey's HSD and I say AOV.mod, it's doing all of those comparisons for me. Okay? And so it's telling me what the difference is between all of those different groups. So the difference between A and B, the difference between C and A, and the difference between C and B. And then it's giving me the p-value associated with that. Okay, so it's actually, in this case, because there's only 3, it's not that far off and wacky compared to when we did the sequential Bonferroni. But this would be the situation where, you know, you're doing the hypothesis testing now, a post hoc test, and you'd say, okay, treatments are significant. And then you do the post hoc test, and you would say, it looks like treatment A and treatment B are different from one another. C and A don't look like they are different from one another. And C and B look like they are different from one another. Okay, so let's do the exact same analysis, but let's just make it more cumbersome. Sorry, but that's life. And so the library that we're going to want to install on your computer and then call here is called multcomp, which is called multcomp because it's doing multiple comparisons. Okay. And I'm going to go ahead and I'm going to set up my model. So here I'm going to say treats. I'm going to be explicit and say that treats are a factor. And then I got my model, right? Just like as before. And so now I'm going to want to, once again, create an AOV object because that's what it's going to want. Okay, so again, it's all the bits except for the hypothesis testing part. And now the function that I'm going to use from multcomp is called GLHT, which is General Linear Hypothesis Testing. And so I'm going to create an object called Tukey.HSD. I'm not going to overwrite the capital HSD one. I'm just going to create a new object called Tukey.HSD, and I'm going to call up that GLHT function. I'm going to give it my AOV object. And now I have to give it another argument. And the argument I'm going to give it is LINFCT, okay? And that's going to specify the type of linear hypothesis we want to do. And we're going to tell it we want it to do multiple comparisons, MCP. And then we have to tell it explicitly what comparisons we want to do. So treats, and I want it to give me a Tukey. Okay, so that's all the rigmarole that goes into that. Ignore that warning message. Okay, and so if I just look at that object, it's giving me the hypothesis that A and B are the difference between A and B. So B minus A is super duper equal to 0. And then here's the actual estimate of how different they are from one another. Once I have that object, if I were to say summary of that object, not that number, it goes ahead and it does the Tukey's HSD comparison. Here it is. It's the exact same p-values that we got when we used the built-in Tukey HSD function. 0374, 0374, 05775, 05775, and so on. Okay. Get in the habit of using the multcomp function because as we'll see next time when we have more complex models where maybe we have 2 different types of factors, the GLT function can deal with that, whereas the Tukey's HSD function can't deal with that. It can only deal with it with this really simple example that we've been playing with here, which I guess I could mention is traditionally it's just called a simple one-way ANOVA. And it's called one-way ANOVA because we only have one kind of grouping of categories that has their own factor levels, but we don't have more than one. Okay, so that's Tukey's HSD, and that's if we don't have any a priori idea about what we want to do comparisons of. So let's say that we did know, I'm going to mention one other thing. Yeah, because we might as well make sure that we understand how we're doing the like if we were to plot this, right? So we have our Tukey's HSD, which is somewhere right there, right here. And so the first thing, like imagine that we had a graph, right? Because ultimately that's what we would have. A, B, and C, and let's say just to, all right, a little bit of a technical difficulty, of course. So we have our response, whatever we were measuring here, right? And we have our data. So we know that A is roughly, let's say that's 59. Okay, so maybe that's our bar plot, our mean and our standard error, okay? And then for treatment B, we know that that's a little less, and treatment C was a little bit more. And so normally when we would be plotting something like this, and we would want to summarize our results from a Tukey test, a common way to do that is to put letters above here to indicate which ones are different from one another. And so if we look at our p-values for our Tukey here, so A versus B, they are different from one another. So one option is you could go ahead and you could just say A and B. And then we go through here. C and A are not different from one another. A. And C and B are different from one another, and they have different letters. And so basically all you would say is that the letters indicate significantly different based upon a Tukey's HSD. You'd also want to say significantly different, parentheses, alpha equals 0.05, because significance is always in the eye of the beholder. But this is how you would go ahead and you would present these types of data. Right. Okay, so let's say that you didn't want to do all the possible pairwise comparisons, that you had maybe a reference group that you were interested in comparing things against. So a really common one might be a control versus two different treatments, for example. And so just playing with our data here, let's say that we wanted to compare, I disappeared. Float on top, Jim. Okay, now I'm floating. And so if we wanted to compare, let's say, everybody against A, for example. So I wanted to know if A was different from B, and I wanted to know if A was different from C, but I explicitly did not care if B were different from C. So I would want to do a test which is called a Dunnett's test. Okay? And a Dunnett's test allows you to do all the comparisons against a reference group as opposed to all the different comparisons. And it ends up being a little bit more powerful because when we did the Tukey's test, we had 3 comparisons that we were making. If we do it as a Dunnett's test and say that we want to compare B against A and C against A, then we're only doing 2 comparisons. So we should have more statistical power. Okay? And so to do that, this is where we will use that GLHT. So I'm going to go ahead and just copy and paste this, and I'm going to recreate this object, and I'm going to call it Dunnett. And I'm going to do the Dunnett. And so I'm going to say the treatments, and I'm going to tell it that I want to do a Dunnett. D-U-N-N-E-T-T. I should probably just spell it correctly there too. Okay, Dunnett. No, I didn't do it. Now I've done it. Okay, so I've now told the GLHT function that I have my model, and I want it to do a Dunnett's test. And so I go ahead and I do a Dunnett's test, and then I say, what's the summary of my Dunnett HSD? And now you can see that it's only done 2 comparisons. It's compared A versus B, which is significant, and it's compared A versus C, which is not significant, okay? B versus A here, the p-value is 0.02. When we did it as a Tukey's, it was 0.03. So you can see that we have a slightly lower p-value when we do it as a Dunnett's test. That implies that we have probably a little bit more statistical power. And the reason why we have a little bit more statistical power is because we're only doing 2 comparisons instead of 3 comparisons. And so there might be an easier way to do this, but as a default, that GLHT function, when we're doing a Dunnett's test, it'll always take the lowest factor level, so the one that ended up being the intercept, and it'll compare everything against that. And so, for example, if we wanted to compare, let's say that C was our reference group. And so that would mean that we would need to change the ordering of our factors. And again, if we go, when we created this as a factor, okay, when we redefined treats as a factor, and we looked at treats, here we have all of our different, codes. or the different groups, A, B, and C, and then it's telling us what our levels are. Our levels are A, B, and C, and it's doing that alphabetically by default. But if we wanted to, say, compare C against A and C against B, what that's going to require us to do is to reorder our factor levels. And so if I were to just look at treats, factor treats, okay, that's telling us what our factor levels are. We could change our factor level orders because an argument that's within factor is called levels. And we could say, okay, what are the levels for treats? And again, if I did it by itself, levels, treats, that's our levels, A, B, and C, okay? What we could do is we could reorder that, right? Because when we call it up that levels, treats, it's giving us a vector of A, B, and C. If we want C to be the first one, we can just rearrange it like we would anything else when we're manipulating data that's in a vector. And so I want it now to be in the order of 3, 1, and 2. And so now the lowest factor level is C. So I'm going to call this new treats. Okay, so now I have a new predictor. I can go ahead and I'm going to make a new model. And that is going to be a linear model, but the response is going to be some function of my treats, of my new treats. Thank you very much. New. There you go, Jim. New treats. Okay, now let's take a look at that model. Notice that things are a little different, right? And that's because now C, since we've explicitly told it we want C to be the first factor level, now C is the intercept, and A has a slope and B has a slope. So it's a little different. Our ANOVA will be the exact same. Our ANOVA results and the sums of squares and mean squared and stuff like that will be identical. It's just we've changed the order. So now we could do a new Dunnett's test. So first we got to create that AOV object, which I will just cut and paste here. AOV new mod is going to be AOV new mod. Okay, so now we have that. And now I'm going to do a new Dunnett's test. And again, the only thing that's different here is that we built the model based upon reordered factor levels. So again, the ANOVA itself, the hypothesis testing part, is the same, but with this Dunnett's test, we have to know what the reference group is. And by default, GLHT, when you ask it to do a Dunnett's test, it'll always take the first factor level. And so we just had to rearrange those. So let's go ahead and we can do that. Oh, what is that all about? Cannot new, oh. Sometimes I think that I want to fail. It is new dot treats. There we have it. And then we can go ahead and say what's the summary of that. And now everything is being compared against C. And so B is different from C, but A doesn't appear to be different from C. Okay. And so that's how you can reorder those factors, and it is cumbersome, but it is what it is. You get what you get, you don't pitch a fit. I'll be honest, I cheat. I don't do this usually. If I wanted C, if C were the control group, I would probably have not called it C. I would have called it something silly like C. And that way I would know that that would be alphabetically the first one, so I wouldn't have to deal with reordering the factors. But just something to be aware of when you're doing the Dunnett's test. So again, the Dunnett's test is super appropriate when you have like a control group and a bunch of treatments and you're interested in simultaneously comparing all those treatments against the control, but maybe you don't care about differences among the treatments. Okay, and now the final type of contrast that we might be interested in doing are what are called planned contrasts. And this is where we do have an a priori hypothesis. Let's say that we were interested in comparing A versus B, B versus C, and A versus B and C or something, right? But we didn't want to do all the possible comparisons. We just want to do a subset of the comparisons. And this is what are called, sometimes they're called orthogonal contrast, but it's just easy to think of them as being planned contrast. And this is another example where we can use the GLHT function. And of course, there's always gonna be more involved. So the first thing that we would have to do is we would have to tell the function what things we want to compare. So let's say that we've done the ANOVA and we're only interested in comparing A versus B. I don't know why we would do that, because then obviously we would have done a t-test, but it's hypothetical land. So let's pretend that that's what we wanted to do. So the first thing we would need to do is we would need to define what contrast we were interested in. So let's go back to our mod. Let's go back to the original model. Okay. And so again, treatment A is the intercept, B and C. And so let's say that we were interested in comparing A versus B. So I'm going to just create an object that I'm going to call K for the comparison, spelled wrong. And then I'm going to turn it into basically what will be officially a table, because that's what it's going to ask for. And I'm going to say that A versus B, and I'm just giving it the name. What's happening inside the parentheses does not matter. But I'm going to say that that is going to equal, and now there are three different possible comparisons I have here. I have A, B, and C. If I'm only interested in A versus B, that means I'm interested in the first one being compared against the second one, and I want to ignore the third one. And so I would code that by saying 1, -1, and 0. So overall, this whole thing right now would sum up to 0. But by putting that 1 and that -1 in there, we're telling it that those are the two things that we want to compare against one another. And so I'll go ahead and I'll do that. I've created that object. There it is. It's as a table, which is why even though there was only one line of that vector, I had to say rbind. AB is just simply the name of the row here. And so I will go ahead and I will do a planned contrast. Okay. GLHT. I'm going to give it my model. And then I'm going to say, well, it's definitely going to be a linear hypothesis that I'm interested in doing. It's going to be multiple comparisons where treats are going to equal K. Okay, so instead of giving it Tukey or Dunnits, now I'm giving it the actual matrix that it's going to play with, which is telling it what comparisons to do. So I go ahead and I do that, and now I can say, what's the summary of that? Summary. And there's the comparison between A and B. And if we compared that against, say, the Tukey, that's even a smaller p-value. But that's because now we've only done one comparison. Okay, so we didn't really, we have a lot more power if that's all we wanted to do was A versus B. And so one nice thing about these planned contrasts is you could say, well, what if I wanted to just compare A versus B and C combined together? So not A versus B and then A versus C, but I just wanted to do A versus BC combined. Well, we could easily set that up by, again, going back to our matrix here. So this is going to be A versus BC. And that, again, that's just a row name. So I'm going to say A is +1. And then for the next two, I'm going to say -1. And I'm going to say -1 because that's, I'm grouping the two negative ones together versus the +1. It can be a little misleading maybe to kind of eyeball that and understand why that coding is going on that way. And that's because R is actually going to do some of the thinking for you. Formally, what the computer is basically going to do in the background is it's going to change that into -1/2. Because the whole thing is going to always sum to 0, right? Just like it did here. 1 plus -1 plus 0 equals 0. 1 plus -1/2 plus -1/2 equals 0. So this is actually what the computer is doing in the background. Back in the old days, you would actually have to do that. But the function is now flexible enough that it knows what the heck you're talking about, so it'll do it for you. And so all I would have to do then is pop that new comparison matrix into the GLHT function. And then I'll go ahead and look at the summary of that. And now A versus B and C combined are not different from one another. Okay? And so this is an example of where it can be pretty handy to use these planned comparisons. We can also give it a table. Again, this was a table, a matrix that we gave it, not a table, but a matrix that we gave it, but it only had one row. And so I just kind of cooked up one where maybe these are the comparisons we want to do. So I want to compare A versus B, I want to compare B versus C, and I want to compare A versus BC combined. Okay, and then that's the matrix that I can go ahead and I can give that GLHT function. So I can just copy and paste this all the way down. And so what do we learn here? A is different from B, B is different from C, A is not different from B and C if they're combined together. Okay. And so this is where planned comparisons can become handy, because you can lump things together and do comparisons, and you can also restrict it only to the comparisons that you're interested in, so it ends up being a little bit more powerful. But it's kind of weird with just this A, B, and C. So as a final example, I cooked up some play data where let's imagine that we are looking at crop yields. Because why not? Who doesn't like to think about crop yields? And so we are interested in the effectiveness of two conventional pesticides, C1 and C2, and two organic pesticides, O1 and O2. And then we have a control group where we've done nothing. Okay, so we've set up an experiment out in the field where we have 5 different treatments, and what we want to know is, you know, do any of these pesticide things, how do they vary from one another? And so let's go ahead and I'm going to make all that data there, and then I'm going to turn it again into something that would look like if you were to upload these data from like an Excel sheet or something like that, so that the data would look something like that. Here's our pest treatment. We got control. We have conventional 1, conventional 2, organic 1, organic 2, and then we have whatever these measures are of yield. Maybe fruit mass, who knows? Okay. And so what do we want to do? So I'm going to reorder this, because if we were to look at these as a factor, oops, oh no, what did I do? There we go. Okay. So if we were to look at our pest treatments as a factor, we can see that the first one is C1, and then control is in the middle. So like hypothetically, if we wanted to do a Dunnett's test, like maybe just compare the control against all 4 of those, of the 2 conventionals and the 2 organics, we would want that control to be the first one in order. So I'm going to go ahead and do that, just so that way our control is the lowest factor level, just for simplicity, if that does make it simpler. I think it does. So I'm going to do it the same way as we did it before, where I'm just going to basically say that pest treatment is going to get, here you've noticed I did lowercase pest treatment instead of uppercase pest treatment, so I'm not writing over the original data. Pest treatment, and then I'm just, here I'm reordering the factor levels, so that way the third one is the first one. The third one is control. I want control to be the first one. And so I can go ahead and I can do that. And now if I look at pest treatment, you can see that there's my 5 factor levels, but the first one now is control. So let's go ahead and let's run a model. It's going to be a linear model where we are thinking about what? We are thinking about yield as being some function of our pesticide treatment. Okay, here's our model. There's our parameter estimates. Again, the control is the intercept. And so just eyeballing this, it looks like conventional 1 is on average 8 better than the control. Conventional 2 is 9 better than the control. Here's organic 1 and organic 2. So it looks like all of them were better than the control. Certainly looks that way. And so you could go in there and just simply say, I want to do a Tukey. I just want to do a post hoc test and see exactly what's going on. Well, I guess the first thing you'd want to do is, let's do some hypothesis testing, shall we? Ooh, significant. Okay, there's some effective pesticide treatment. Let's go ahead and try it as a Tukey. And I will go ahead and I will do that. And then I will say summary of my Tuk. And here's all of the comparisons, and here's all the p-values. So again, it looks like everybody is different from control. It doesn't look like the conventionals are different from one another. There's some marginal, weirdness going on here. That one's just like a mess type thing. But this is doing all the possible comparisons. Maybe we just want to see how different everybody is from the control group. And so again, we could do that by just putting done it in there. Is it capital D done it? I bet it is. Yes, it is. Darn it. Unprofessional. Done it. And then I'll do, let's call this a done. The done it. And then I'll do the summary of the done it. Create that object. Done it. Done. I spelled it wrong. Done it. All right, so now we're comparing everything against the control, and we can see that all of them are clearly different from the control, which is the same thing we saw when we did it as a two key, right? So that's not entirely surprising, because if anything, the done it should be more powerful than the two key. But if it's significant at two key, it's certainly going to be significant as a done it. But now let's say that we don't want to do all those possible comparisons. Let's say that we had it set up and we were hired or got grant money or something from somebody that wanted to look at these comparisons. We wanted to say, well, how different is the control from the conventionals as a group? How different is the control from the organics as a group? And then maybe we're interested in knowing, is organic 1 different from organic 2? And then maybe we're interested in knowing whether or not conventional is different from organic. And so there's only 4 comparisons that we want to do here. So that should give us a lot more statistical power than when we did it as a two-key, where we had what? We had 10 different possible comparisons. So maybe this is what we want to do, and this will be our matrix that we will then put into that GLHT function. And I will call this planned contrast. And then I will do a summary of my planned contrast. And what do we learn? Well, we learned that we have a lot of statistical power compared to that two-key test. So what do we got? Conventionals, clearly you get bigger fruits if you are applying conventional pesticides as opposed to nothing. It's also pretty good to the organic ones. They are better than the control group. So we've tested those 2 hypotheses. Now we can ask, is there a difference just between those 2 organics? Well, according to this, we would reject the null and accept the alternative that indeed organic 1 appears to be different from organic 2. If we compared that against our two key, somewhere up here, organic 1 versus organic 2 is here. Oh, it doesn't hit that magical threshold of 0.05. But again, that's because we're doing 10 comparisons. Here, we're only doing 4. We got a lot more statistical power, and we're able to, staying within the type 1 error rate that we are comfortable with, which is 0.05, we are able to say these 2 organics are actually different from one another. And then the conventionals grouped together versus the organics grouped together, it appears as those 2 are different. And if we went back and we looked at the parameter estimates, it's pretty clear that the conventionals appear to be doing ever so slightly better, but statistically significantly better than the organic pesticides would. So that's a bit more of a realistic, I guess, kind of an example of where you would use these planned comparisons. But they can be nice and they can be pretty powerful. So that's post hocs. And hopefully over the course of this hour and whatever minutes, I've convinced you that an ANOVA, as it's classically known, is nothing more than a multiple regression. And yeah, and so why don't we think about that a little bit and play with it, and I'll end it with a really nerdy, lame dad joke.